Hey, welcome to this video on inequalities. This is a video on rational inequalities. So in order for us to solve a rational inequality, we have to first and foremost always start with a domain. So this is the domain, and domain is always established by looking at the denominator. So since x plus 1 is your denominator, by setting this equal to 0, you will conclude that the restricted value is -1. So -1 would make it 0. So this is why domain consists of all real numbers such that x is not equal to -1 already. So the first method that we'll discuss here is to solve this by eliminating the denominator. Many of us don't like seeing fractions. So that's the first thing that we have to take care of. The second very important step is to be aware of the following rule. If you choose to multiply an inequality, any type of inequality, by a number, you want to make sure that that number is a non-zero value. So that's the first thing. It is always positive. The reason for that is so we want to maintain the inequality symbol throughout the questions. We don't want to flip-flop with this because we may lose track and then find wrong solution to the inequality. So when you say eliminate the denominator, that means I have to multiply both sides of this equation, inequality, by common denominator, and that denominator must be always positive. So this is why, since my choice here is x plus 1 squared, the denominator is x plus 1. When you square it, it is guaranteed to be positive always. Of course, -1 is not part of the solution because it's excluded from the domain, so don't worry about this -1 for now. So, multiply both sides by x plus 1 squared. So the right-hand side will be obviously 0, because you have 0 times something, and it's 0. When you, however, work with the left-hand side, very nicely you will simplify x plus 1 and eliminate the denominator. So this is why you have now factored form, quadratic type of inequality. And since you're already an expert in solving quadratic inequality, because you watched the first video, so now you understand that this solution is as follows. You can recall the behavior of a quadratic function. Leading coefficient is positive, so opens up on both ends. This is why you see the sine function that starts from above to the left from -1. Then you go below x-axis and then go back up and continue staying above. Which means, in order for you to be greater than 0, you do not include those 0 values. So 0 itself is not included, and -1 is not included because -1 is not part of the domain. So it can never be part of a solution. 0 cannot be included because you can show possibilities for being greater or equal to 0, just being greater than 0 in this case. So interval from -1 to the left, not including the endpoints, or from 0 to the right. So this is why you see this or that using inequality statement, or interval notation, x is element of -infinity and -1, union, which reads or, x is element of the interval 0 to +infinity. So that's first method. The second method here on the screen, we can use the test values approach. So first find all critical values where numerator is equal to 0, so that gives you only when x is equal to 0, and find all critical numbers where the denominator is equal to 0. Since the denominator is x plus 1, so that is equal to 0 when x is equal to -1. I know he's saying -1 is not part of the solution. It is not part of the solution. Just find those critical numbers first, which means your entire domain will be split into 3 different regions. So the split comes from the critical values, -1 and 0. Neither are part of the solutions, neither values. -1 because it's restricted, and since we are looking for values that are supposed to be greater than 0 for this in our inequality, so we're not including the x-intercepts. So having 3 intervals in place, numbers that are less than 1, numbers that are in between -1 and 0, and numbers that are greater than 0. Arbitrarily pick any value that fits into each region. So this is why x minus 2 was chosen. Find the value of the expression when x is equal to -2 of your rational expression. So you have here you see the calculation, so it gives you positive reading. Boom. So you know that the graph will be found above x-axis. When you pick a number from the second interval, x is equal to -1/2, you do the calculations and the value of the rational expression is negative. So the graph has to fall below. So you will see this change of behavior going through -1, not including -1. Okay. Continuing below x-axis, not including 0. And further, for the last interval, you select 1 or any number that is greater than 0. You do the calculations, it's positive, so this is why you have to continue moving or staying above x-axis. So the solution is less than -1 or greater than 0. Using interval notation, this is why you see this statement right below. So this is example number 1. Example number 2, slight step up. Why? Now we have an inequality where we have linear expression on top and bottom, and this is less than a number. The previous one had with relation to 0. So first thing you do, domain. Look at the denominator. X minus 1 is equal to 0 when x is 1, so this is why you have to get rid of 1. So the value of 1 will never be considered as a part of the solution. The symbol of inequality is less, so you will not include the endpoints. Those are the key things that you have to pay attention. First, approach eliminating the denominator. So since you know both sides are to be multiplied by positive value, common denominator in this case is also x minus 1. So this is the choice that you have, that x minus 1 squared is positive, is guaranteed to be positive because that binomial squared, no matter what goes inside, to the power of 2, positive. Bingo. So we have now opportunity to simplify. So this exponent with that exponent will give you x minus 1. Copy x plus 2, x plus 1 of course, less or equal, and then -1 times this binomial squared. What you see here is a difference of squares application. A squared minus b squared is equal a minus b times a plus b. So this is a plus b. So this is the formula that we employ to simplify that. if you're not familiar with difference of squares, all you have to do is just FOIL. Expand it nicely, simplify, you will get x squared minus 1. Then binomial expansion. So x minus 1 squared simply means multiply it by itself twice. You do it, you distribute negative sign to each term, so this is why you see that. Negative x squared plus 2x minus 1. The same strategy now is being used as for other types of polynomial inequality, which means collect like terms, x squared and negative x squared on opposite sides. So bring that negative 1 x squared to the left side. So this is why you have 2x squared. Then you have linear term, positive on that side, negative on the opposite side. And negative 1 and negative 1 cancel each other out, same value. So this is why you have 2x squared minus 2x is less than 0. Now we can divide by 2 because this is a common factor. So this is why you would get x squared minus x. Take out the common factor. So to have an inequality in factored form is the best possible place to be. Look at the binomials. Both are linear. So this is the quadratic application. Leading coefficient is positive. If you were to expand it, you have x squared minus x, and you know that right from here. So both parts of parabola open, both arms are directed upwardly, and you know that 0 would be the x-intercept, 1 would be the x-intercept, but it is really not because of the domain, but we can assume that it would be. So positive part of the graph would be found on this interval where x is less than 0, or when x is greater than 1. In our case, we have to solve for all values of x that are less than 0. So this is why your choice will be to select this negative part of interval between 0 and 1. You don't include endpoints because you are maintaining this inequality of being less. So this is why you have x is in between greater than 0 and less than 1. Using interval notation, this is why you see x is element of the interval between 0 and 1 open brackets. There you go. One more example with a little bit more complex question. So let's move on. The same example, apparently, solving it slightly differently by rearranging first. So the same equation, and it's done by changing terms around, shifting terms around, and simplifying it. So when you put negative 1 to the opposite side, this is why you see this rational expression plus 1 is less than 0. The next step, find common denominator. So your 1 can be expressed as x minus 1 divided by x minus 1. So this is why x minus 1 is a common denominator, and this is why you have plus x minus 1 on top. Identify like terms. So x plus x gives you 2x, 1, and negative 1, 0. So this is why you have 2x divided by x minus 1. So the second approach is using test values. Rather than eliminating the denominator, we will be using test values. So find critical numbers. The top is 0 only when x is 0. Makes sense. 2x is equal to 0 when x is equal to 0. The bottom part is equal to 0 when x is equal to 1. So now your set of real numbers is divided into 3 regions. Less than 0, in between 0 and 1, and greater than 1. Use test values. So this is why we use negative 1 as a part of that interval, and the value of the rational expression is positive, so this is plus sign. When you substitute negative positive 1 over 2, you get negative reading, so the graph is expected to be found below x-axis on that interval. Last one, x is equal to 2, positive value for the rational expression, therefore the graph is expected to be above. Since you're finding the solution where the left side is less than 0, this is why your graph is, the part of the graph that you consider is on the interval 0 and 1. This is the same example just solved in a slightly different way, so solution has to be exactly the same. Already. One more. Look at this. Rational inequalities, and you see one rational expression and then linear expression on the opposite side. Now you have to find the solution where the left side is greater or equal. So the endpoints is the possibility. Pay attention to that. Possibility, that doesn't mean that you always have to include the endpoints. And you will see the reason why. So, as I said, domain, so step number 1. Ta-da! So find the domain, and we'll use this method, eliminating the denominator. Yes, you can use the other method as well. I would highly recommend that you do it yourself and see if you get the same result, and you should. You should never give up. You always try to do more and more to master your skills. So eliminating the denominator. Again, you multiply both sides by positive number. So this is why you say x minus 1 squared becomes the positive value that you multiply this inequality. So conveniently, this is the binomial where this exponent and x minus 1 to the power of 1 would cancel each other out. So you have x minus 1 as a common factor here. X plus 1 is just carrying from the second part of this rational expression. So this is why you have x minus 1 times x plus 1 on the left side. The right hand side, you have to just do it. So first, remember the brackets first, the Bedmas rule. So let's do the exponents first, right? So x squared minus 2x plus 1 times the negative x plus 1 here. We just talked about it not long ago. This is the difference of squares application. If you don't see it, don't worry, you can still expand it. X times x, negative 1 times x, and so on. Eventually you will get to that point where you see x squared minus 1, that simplified version of that multiplication of two binomials. Here you just have to expand it whether you like it or not. So you multiply this negative x by 3 terms inside, and then 1 times 3 terms of the second. So what you do is you get negative x cubed, then plus 2x squared minus x plus x squared minus 2x plus 1. Just simply follow this FOIL method. Be patient here. There is no need for you to speed up things if there's a chance of making mistakes. So just do it patiently and you'll get it. So the left side is as it is. Now you're going to rearrange this and move everything to the opposite side. So cube terms first. The highest degree, that's the leader. Then you copy the x term right here, squared. Then you would bring, not necessarily in the same order, but what you will get in the end, a polynomial with many, many terms, and you have to simplify it. So you have to collect like terms. So this is why you get what you see here, cubic polynomials. So we started with something weird, rational expression, inequality, and we have simplified this into cubic polynomial. So that's the great accomplishment right here. So next step will be to work with that cubic polynomial. Okay, so I just copied this one more time to keep us on tip of our toes. So know that this is the original question. Know that this is the domain. Very important right here. So by inspection, we will find possible solution to this cubic polynomial. Coefficient a is 1, constant is -2. So the possibilities here are the divisor of -2, which is plus or minus 1, or plus or minus 2. And you have only 4 choices here. So just try and error. There is no other secret. It works for x is equal to 1. So x minus 1 is a factor. So now, knowing this, you can divide this cubic polynomial using long division or synthetic division. Doesn't matter. I prefer long division because it always does work for me. So dividing this by x minus 1, you get x squared minus x plus 2, no remainder. Of course no remainder. This is a factor. By factor theorem, the value of 1 for x makes it 0. So now we have changed this expanded form into factored form. Factor 1, factor number 2. So solution here is 1. That would be fine if we were to accept that. And then the possible factors for that quadratic trinomial. Do we have any possible factors here? We can quickly discover this by either trying to use the quadratic formula, or you can try to factor it, which takes time and oftentimes leads to very poor results if you stick with factoring all the time. Quadratic formula always give you the answer to your question. Since the discriminant, which is found as b squared minus 4ac, is negative, is equal to -7, no real roots, which means that you can only have one possible x-intercept for this cubic polynomial. So leading coefficient is positive. So the end behavior starts from -infinity and then the switches to positive infinity. Our inequality says find a solution to this product where it is greater or equal to 0. Since the only x-intercept is at 1, and 1 would be included in our statement, but it cannot be. Reason being, not part of the domain. So this is why, as I said in the beginning, sometimes you don't include the endpoint for your final statement because you have to cross-examine with the domain. Since the domain does not allow you to include 1, this is why your statement must say x is greater than 1, not equal. Using interval notation, x is element of 1 of the interval starting from 1, not including 1, comma, positive infinity. I hope you have enjoyed this long video, but very important video. And this long video gave you some background information on how to solve rational inequalities. So to summarize this, you either have an option to do it by eliminating the denominator or by simplifying it and using the test values. So pick the choice that you like most, that you understand, and stick with your strategy. And you always will be able to find a solution. So thank you for your time. Thank you for watching. I see you next time. Bye for now.